So, in the previous class we were looking at a worked example involving a supersonic diffuser. So, if you recall, this was a converging diverging diffuser designed for operation at a free stream Mach number of, so this was the inlet, this is the throat, and m is equal to 1 at the throat, and the design free stream condition m infinity design was 2, and we calculated the mass flow rate through the intake for design operating conditions, and we came up with the following things. It was also given that for this value of m infinity, we also obtained from isentropic tables for m infinity equal to 2, we obtained that A inlet divided by A throat, we said this was equal to 1.6875. And we also showed that the mass flow rate for design operating condition was 5.832 times P infinity, which is the free stream static pressure, times A throat divided by square root of T infinity, which is the free stream static temperature, and this was multiplied by the following quantity. And we also showed the capture area for this case to be equal to the inlet area. So, A capture for design condition we showed was equal to A inlet. So, if you use the fact that for the design Mach number A inlet over A throat is equal to 1.6875, this can be written as 1.6875 times A throat. Now, we are going to calculate the same quantities for an off design Mach number. So, this is the next part. So, the off design Mach number here we take to be 1.5. How do these quantities change when the Mach number is reduced to 1.5? This means that the intake is actually trying to swallow less amount of mass than design operating condition. So, usually in this case what happens is there is a normal shock which stands in front of the intake. So, normally the shock is something like this. So, it is a curved bore shock which looks something like this, and the flow comes through the so these are the free stream conditions, and the flow comes through and then goes through the intake in this manner. We can assume that the throat Mach number still remains at m equal to 1, and so what we need to do is calculate the mass flow rate which goes through the diffuser in this case. This is going to be reduced. We assume this to be a normal shock. For our calculation purposes, we take this to be a normal shock. We ignore the fact that it is actually a curved bore shock. For analysis purposes, this is a good approximation. So, we have a normal shock which stands at Mach 1.5, and then we have isentropic flow that goes through the intake. Okay. So, let us go ahead and calculate the properties. The formula for calculating the mass flow rate through the diffuser is the same. Only thing that has changed is the P naught has changed now because of the loss of stagnation pressure across the normal shock wave. So, let us go ahead and do that. So, the mass flow rate m dot with m infinity equal to 1.5 comes out to be P0 inlet times A throat divided by square root of T0 inlet times square root of gamma over r 2 over gamma plus 1 raised to the power gamma plus 1 over gamma minus 1. So, from normal shock table, for m equal to 1.5, we have P0 inlet, which is after the shock wave, divided by P0 infinity, which is the stagnation pressure ahead of the shock wave. Right? The ratio of stagnation pressure comes out to be 0.929787. Okay, and from isentropic table, for m equal to 1.5, we have P0 infinity over P infinity equal to 3.67103 and P0 infinity over T infinity equal to 1.45. So, I can use the same trick that I used before and write P0 inlet as being equal to P0 inlet divided by P0 infinity times P0 infinity divided by P infinity times P infinity. So, if I substitute the numbers, I get this to be 3.4133 P infinity, and similarly for T0 inlet, I can do the same thing, P0 inlet divided by T0 infinity times T0 infinity divided by T infinity times T infinity, and there is no change in stagnation temperature across a normal shock wave. So, T0 inlet is equal to T0 infinity. So, this is 1 and I can substitute for these other quantities and I get this to be 1.45 times T infinity. So, m dot for a free stream Mach number of 1.5 now comes out to be 2.8346 times P infinity A throat divided by square root of T infinity times it now becomes clear why we wrote everything in terms of the free stream static quantities, because although the Mach number has reduced, the free stream static pressure, free stream static temperature remains the same. We are only looking at a reduced speed for the intake, which is why we wrote everything in terms of P infinity or static conditions here and also in terms of static conditions here. So, we are assuming that static condition remains the same, I have only reduced the speed of the intake. So, I can make a comparison between the two and I can see that there is a reduction in the mass flow rate between these two cases. So, if I see now m dot m infinity 1.5 divided by m dot design, I can see that this is 0.486. So, the mass flow rate has reduced by about nearly 50% and static conditions have remained the same. Okay. Now, let us try to calculate the capture area for the intake in this case. Notice that the capture area, we expect the capture area to be less in this case than in the previous case. in the previous case, as you can see from here, the capture stream tube would be like this. So, the capture area in the free stream is equal to the inlet area. Whereas, in this case the capture area is going to be less, because you see that this is the stream tube that passes into the intake. So, that means the capture area here is going to be less in this case than in the previous case, and that is what we are going to calculate. But if I consider the stream tube and I take a section here, which let us say I call as the section infinity, and this is the inlet, right, this is the inlet. I can equate the mass flow rate between these two sections, because it is a stream tube. The same amount of mass passes through the stream tube here and the stream tube here. So, by equating the mass flow rate, I can actually calculate the capture area, and that is what I am going to do next. Okay. So, let us see how we do that. Yeah.
After normal shock, flow will be subsonic.
Correct.
And again it will accelerate in this one.
Convergent portion.
Mach number will be supersonic then.
No, we are maintaining the exit pressure in such a way that it need not always accelerate, you know. The exit pressure.
But we are telling it is choked at m is equals to 1 at throat.
It is choked here also at m equal to at the throat.
Yeah, but in this intake Mach number is supersonic. In this
Correct.
intake Mach number is subsonic.
Yeah, but I can maintain a downstream condition which will ensure that the flow decelerates to a subsonic Mach number. The downstream condition is determined by what the combustor wants, for example. If I want reduced mass flow rate, then the pressure here will be higher, correct? So, that means the flow will automatically come out the way the component further downstream wants this to be, okay. So, that will be taken care of, that is not an issue. So, we equate the mass flow rate that passes through the section labeled infinity is going to be nothing but rho infinity u infinity times A infinity, where A infinity is the capture area, right. So, this is the capture area that we are going to calculate. So, if I rewrite rho infinity as P infinity over R times T infinity and U infinity as M infinity times square root of gamma R T infinity, so this can be simplified to read like this. P infinity times M infinity times A infinity divided by square root of R times T infinity times square root of gamma. So, this becomes, we are going to set this to be equal to m dot corresponding to M infinity equal to 1.5, right. So, the same mass flow rate that passes through the stream tube at this section will also pass through the stream tube at the inlet as well as the throat section. So, the mass flow rate remains the same because it is the same stream tube, right. So, I equate this expression to this expression, and you can see that there is a nice cancellation of terms. The P infinity drops out, right. The square root of gamma divided by square root of R also drops out, square root of T infinity drops out. So, we get a nice expression which tells me A infinity divided by A throat is equal to 2.8346 divided by M infinity times so this is equal to 1.1. right. So, this is the capture area. So, A infinity divided by A throat is 1.1 in this case, and if you remember, for the design condition the capture area A infinity divided by A throat would be 1.6875. So, you can see that the capture area has indeed decreased when we reduce the Mach number. The next thing that we are going to do is to see whether even in this off design operating condition, if I increase the throat area like we discussed yesterday in the previous class, if I increase the throat area, can I make the shock disappear so that I have a shock free operation even under design operating condition. In other words, what should be the throat area for the shock to be completely swallowed, and once it is swallowed, what should be the throat area for steady operation. Remember, we said that for swallowing the shock, the throat area should be a certain value. Once it becomes shock free, then we should reduce it to a value which is compatible with isentropic shock free operation. Okay, that is what we are going to do next. So, if you remember, we derived the following expression. So, for shock free operation, or let me rewrite this way. For swallowing the shock, let me put it this way, we are looking at two situations. For swallowing the shock, we must adjust the area so that the loss of stagnation pressure due to the normal shock is accounted for in the throat area, right. So, in this case we say that for swallowing the normal shock, A throat divided by A throat design is equal to P0 throat under design condition divided by P0 throat, and the Mach number becomes 1.5. And this is going to be, what is this ratio going to be? As we calculated before, it is basically going to be the ratio of the mass flow rate. So, it is going to be 1 over 0.486, which is 2.58. Remember, static conditions remain the same. So, that means we need to relate these things to the static quantities. P infinity and T infinity remain the same. So, we need to relate this to the conditions which are remaining constant when we evaluate this ratio. This is not simply the ratio of stagnation pressures across the shock wave, because the speed has changed, the stagnation pressure upstream has also changed. In other words, P0 infinity for the design case is not the same as P0 infinity for the off design case, correct, because the speed is different. Otherwise this would simply be P0 the ratio of stagnation pressures across the shock wave, okay. So in this case, because the static conditions remain the same and stagnation conditions change, you need to make sure that this is calculated properly, okay. Do you understand that? If you remember, we wrote down earlier that for the normal shock, from the normal shock wave table, we wrote down the following quantity, right, P0 inlet divided by P0 infinity, we said was 0.929787. If P0 infinity is the same in both cases, then this would have been 1 over 0.929. It is not 1 over 0.929 because P0 infinity is not the same in both cases. P infinity and T infinity are the same in both cases. So you need to relate this to that and then evaluate this ratio. That is why the number in the denominator is not this but 0.486. Alright. So this is how much the throat area has to be increased to swallow the shock. Once the shock is swallowed, right, now we have a situation where the Mach number is the inlet Mach number is 1.5, correct. Once the shock is swallowed, so this means from isentropic table, A inlet divided by A throat corresponding to this Mach number, A inlet divided by A throat is going to be 1.17617. So A inlet M infinity equal to now becomes, I am sorry, let me write it in terms of A throat. So A throat, we are changing the throat area. So A throat corresponding to M infinity equal to 1.5. Now from this comes out to be A inlet divided by 1.17617. But we also know for the design condition, from design conditions we know that the inlet area is 1.6875 times the throat area under design operating condition, right. Inlet area remains the same. The inlet area remains the same in all the cases, only the throat area is changing. So that means I can replace this like this, A inlet is 1.6875 times A throat under design operating condition. So which tells me that A throat M infinity equal to 1.5 divided by A throat design is equal to 1.6875 divided by 1.17617. So I get this to be 1.435. Okay. So, what this is telling me is if I keep the throat area the same, even in the off design operating condition, there will be a normal shock and a loss of stagnation pressure if I keep the throat area the same. However, if I increase the throat area to a value which is equal to this, then the shock is swallowed. Once the shock is swallowed, I then reduce the throat area to this value so that I can continue to operate shock free in an isentropic manner. Okay. Notice that we have consistently calculated everything in terms of the throat area under design operating condition. So, everything is around that, and the static conditions, free stream static conditions remain the same. Okay. These are the two important things. Yeah.
Capture area will be same now to design the condition and this.
Yes. Now capture area will be the same because it is completely shock free. Capture area in this case, if you operate in this manner, will be the same. Correct. So, that completes our discussion of this worked example involving supersonic diffuser, and what we are going to do next is look at interaction between fan of flow and nozzle flow, or Rayleigh flow and nozzle flow. Remember, we talked about fan of flow separately, we talked about Rayleigh flow separately, we have talked about nozzle flow. Now we are going to look at interactions between these two, because in any real life applications you always have these kinds of situations, a duct preceding a nozzle or a duct following a nozzle, there are friction effects, heat addition and so on. We are going to look at that next. So, we are going to look at interaction between nozzle flow and Rayleigh and fan of flow. Interaction between nozzle flow and fan of flow is easy to see. So, we will do that, but the ideas and concepts extend in a straightforward manner to Rayleigh flow also, and we will try to do that through a numerical worked example. So, the concepts become clear. Okay. We will discuss the theory for interaction between nozzle flow and fan of flow. So, we first start with a situation where we have a pipe or a duct, constant area, followed by a nozzle. So, we have a pipe or a duct followed by a convergent nozzle, because we will also look at the situation when this is a convergent divergent nozzle, that is also possible. So, first let us start with this. So, we have flow which is coming through like this, and I am going to mark this state here as 1, here as 2, and this of course is the throat section. So, let us assume that the friction factor in this case is F, and the flow in the nozzle is always isentropic. The friction effects are important only in the constant area portion, and the flow in the nozzle is isentropic. If this is the case, then I can sketch the process from 1 to 2 to throat the following way on a TS diagram. So, if this is the TS diagram, let us say this is my state 1. So, this is T1 and this is P1. So, this is P01 and this is T01. So, this is my stagnation state corresponding to static state 1. And now, we are actually following a Fano line in this case. So, this is the Fano line corresponding to this mass flow rate. And my T star is, this is my T star, this is m equal to 1. So, I go from state 1 to state 2 along a Fano line. Right. So, I go from here to here along a Fano line, and from 2 to the throat section, this is an isentropic flow. So, that means I go from there to the throat section in a vertical line. Right. So, I go from here to here along a vertical line. So, this is my throat section where we expect the Mach number to be 1 unless otherwise specified. Okay. So, I go from 1 to 2 along the Fano line, and then I go from here to here along an isentropic path. Now, the most important consequence of adding a pipe or a duct before the nozzle or even after the nozzle has to do with the reduction in mass flow rate through the nozzle. Okay. So, if I write the expression for the mass flow rate through the nozzle, you remember this is nothing but P0 nozzle A throat divided by square root of T0 nozzle followed by this term now. If the pipe or the duct were absent, if it was not here, then the stagnation pressure for the nozzle would be the same as the stagnation pressure over here, P01. So, in the case if there is no pipe or duct, then this would be the P0 nozzle would be equal to P01, right, P01 times A throat divided by square root of T01 times this quantity under the square root. Now, when the pipe is present, so this is T01, when the pipe is present, this becomes P02 times A throat divided by square root of T02 times this. Right. The isentropic part of the flow starts from station 2, which is why I have written T0 nozzle as T02 in this case. So, because of the presence of the pipe, we can see that P01 is going to be greater than P02. Stagnation temperature remains the same in a Fano flow. So, there is a reduction in the mass flow rate due to the presence of the pipe. Okay. The other important point is, notice that m equal to 1 in this case is attained here, okay, which means the value of m at the end of the pipe will always be subsonic. If inlet is subsonic, this will always be subsonic because m equal to 1 can occur here only. We cannot have m equal to 1 here. So, if you make this very long, more than L star for this, then there will be an adjustment of the mass flow rate and inlet condition, so that m is always equal to 1 here and not here, okay. And the reduction in mass flow rate, of course, is also another important aspect in this. So, there is a reduction in the mass flow rate as a result of this. So, when you design a nozzle for a particular mass flow rate and stagnation pressure, and if you connect it to a reservoir, you need to take this effect into account, the reduction of mass flow rate as a result of this. Okay. We will illustrate these concepts also using numerical values once we complete the discussion of the theory. So, this is one situation. The second situation is the following. Situation 2 is when we have a nozzle and then a duct or a pipe is connected downstream of the nozzle. So, this is the nozzle and so I am going to call this section 1 and this I am going to call as section 2. And this of course is the throat section. So, if I sketch the process curve for this situation, then the TS diagram would look like this. So, this is state 1 and this is okay, this is T01 and let us say this is T star corresponding to T01. Then the flow goes from state 1 to the throat in an isentropic manner, but notice that in this case the Mach number can never become 1 at the throat section, because there is a pipe which follows the throat section. So, this nozzle can never choke when you attach a pipe like this. You can have m equal to 1 at the end of the pipe, but not at the beginning. Okay. So, which means that the process line follows something like this. So, this is my throat, I come up to here and then I get on to a Fano curve which looks like this. So, I go from here to here, this is my throat section and then perhaps I go from there to there, right, like this, and this could be state 2 or state 2 could be anywhere else, that is also possible. So, you can have Mach number at state 2 to be 1 or maybe even something less than that, maybe state 2 can be here as well, that is also possible depending upon the back pressure conditions and the length of the pipe, friction factor and so on. Okay. But notice that m dot through the nozzle, what will it be? Will it be less than or same as before? In this case, in the previous case it was less. What will it be in this case?
Depends on exit is choked or
depends on whether the exit is choked or not. But keep in mind that for a given value of stagnation pressure, ambient pressure remaining the same, if the pipe had not been there, then most likely the nozzle would be choked. If the stagnation pressure, so let us make the following statement. let P01 divided by P ambient be greater than 1.829. Okay. That being the case, if the pipe had not been there, then the flow through the conversion nozzle would have been choked, right, and the mass flow rate would have been equal to, so m dot nozzle no pipe would be P01 times A throat divided by square root of T01 times the quantity under the square root. Now, if I remove the pipe, then the mass flow rate, I am sorry, if I add the pipe, then the nozzle becomes unchoked. That means the mass flow rate through the nozzle is going to be less than what it was before, correct? Since the nozzle is in this case. So, the nozzle is choked if the pipe is not connected. Connecting the pipe unchokes the nozzle so that the mass flow rate decreases. So, what is important in these types of situations is the practical implication, right, both in this case and the previous case. You assume that if I have a nozzle, this supplies a certain mass flow rate, I connect a pipe, you expect the mass flow rate at the outlet to be the same as the previous case, but you realize that it is not going to be the same, right. So, you have a compressible flow equipment, let us say a test section or something else, you want a certain mass flow rate, so you design a nozzle to give you that Mach number and mass flow rate. Now, when you connect the pipe to it and take it to the test section, you realize that the mass flow rate is no longer the same and the Mach number is also no longer the same perhaps. Okay. So, that is a very important thing, that is why these problems are very important from practical situations. Okay. All right. The next interaction that we are going to look at is combination of fan-off flow and a converging diverging nozzle. So, when you connect a converging diverging nozzle to either a pipe before or after, then you can get into situations where you have normal shock standing either somewhere in the duct or perhaps in the diverging portion of the nozzle itself, depending upon the flow that is under consideration. We will discuss this in the next class.